secretive thing because it just takes too much time. We'll only do it for the attendance. All these questions are over. So let's just go by a show of hands. First question, MDPs address dynamic environment. How many of you think that's true? Okay. How many think that's false? Most of you are not thinking at all. Okay, so we think that next, MDPs address partially observable environments. MDPs, the ones that we just started talking about last class, and that we do a fire example of, worked out example. We'll go more into detail today, but I just want to see where they will MDPs address partially observable environments. How many of you think that's true? How many think that's false? Okay. So the answer for this, it turns out, is essentially MDPs themselves are actually just looking at fully observable environments. The assumption is that when the agent is in a given state, it knows what state it is in. And that's how then it decides what action to do there. Okay, there is an extension of MDPs called POMDPs, partially observable MDPs, which actually consider partially observable environments. Okay, so MDPs are actually far fully observable environments. It becomes clearer. It's not surprising if you didn't realize it by now, but it's a common mistake. In fact, they don't do partially observable, they do actually fully observable. Okay, for partially observable, you have to do POMDP. And similarly, something that's a little harder to grasp right now, hopefully it will become clearer as we go along, is MDPs actually don't look at dynamic environments, they look at static environments. Okay, an environment is dynamic if the environment changes when you are not looking at it. Okay, the normal MDP policy assumes that the environment only changes because you did an action. Okay, there are actually, once again, extensions of MDPs called MAMDPs, multi-agent MDPs, or DEC MDPs, decentralized MDPs, or DEC POMDPs, decentralized partially observable MDPs, which handle dynamism. But the simple MDP formalism just assumes that the environment is static. So it assumes environment is static just like A star does. It assumes environment is fully observable just like A star does. Okay, so there are two things that are common with respect to A star already. Okay, the third question is MDPs address stochastic environments. How many of you think that's true? Okay, how many think that's false? Okay, that's good. So that much at least we got. So in some sense, MDPs, the real extension of MDPs over A star search, honestly, is this stochastic ability to handle stochastic actions. So the environment changes only when the agent takes an action. But in the case of A star search, the agent can assume that when I do A in state S, I will get S dash. S dash is a unique state. Right now, when it thinks when I do A in state S, either S1 or S2 or S3 will occur with the following probabilities. That's all it knows. This is during the thinking phase. Okay, in the doing phase, when actually the agent does action A in state S, only one of those states will actually occur. You see what I'm saying? It's sort of like if I'm thinking what will happen when I toss my coin, I have to consider the possibility of what happens when it comes heads, what happens when it comes tails. When I actually toss the coin, it will come either heads or tails, not in between. There is no one of these, standing on its pitch kind of. You see what I'm saying? Okay, so that's an important thing. So this indeed is actually true. The next one is MDPs generalize the notion of goal. True or false? How many of you think that it's true that they generalize the notion of goal? How many think false? Okay, most of you actually don't yet have any intuitions. That's interesting. About MDPs, hopefully that will change. In fact, MDPs do change the notion of goals quite a bit. You know, in a way, actually, remember your parents, told you, especially when you didn't get an extremely good grade or didn't win some particular competition and you came home and were moping, they said it's not the end, it's the journey that matters, right? And it's not just for losers that journey matters. In general, for all of us, journey is what really matters, okay? As you are going to different states of the world, you're getting rewards. Some states get big rewards, some states get small rewards, but there are always rewards. Some can be negative rewards, some can be positive rewards. So MDPs really generalize the notion of what it means. What is an agent trying to do? It's not just trying to go towards a single goal and it doesn't matter what state it goes through. It actually cares about the states it's going through. Now again, when you have a general framework, that's only an option. You don't necessarily have to have rewards that make, you don't necessarily require that MDPs must always have non-zero rewards for every state. Okay? MDPs are strictly general compared to A-star search. So something like A-star search can be modeled as MDPs, where in essence what you will wind up doing is you will say reward is 0 for every state, let's say, except in certain states which are terminal states. In fact, another way of actually, a more interesting way to model it would be that you can talk about the reward system itself. This is something that comes across a little later when we go towards the reinforcement learning. You can think of reward as a function of state, reward of the state S. And you can also think of a reward as a function of state, action, state dash. So when you are in state S, okay, that should be R. When you are in state S and you do an action and get into state S dash, you get a real number. That's your reward. The reason this is interesting is if you use this model, you can see how A-star search can actually be a special case of MDPs. Remember, when you do an action in A-star search, there is a cost to the action. Where do you capture the cost of the actions? You can capture it this way. RSAS dash would be the cost of the action. In fact, it's way more general than what you really need, because all you really need in A-star search is the cost of action A. The cost of the action doesn't depend on which state it is doing, which state it's being done in, and which state it actually needs you to. But if I give you this function, you can essentially get cost of an action. You can model that using cost. You can model the cost of action using this function. You guys see that? Okay, so one of the things that I want you to understand as we go along is MDP is a huge generalization, but at the same time it's not the full generalization to handle all possible environments. Okay, it generalizes, for example, stochastic. From deterministic you went to stochastic environments. You went from goals of achievement, where all that matters is reaching a particular state and nothing else, to general reward structures where the journey itself essentially gives you rewards. And when you did that, actually A-star search will still be a special case of MDPs where environments are actually deterministic. Deterministic is a special case of stochastic. And similarly, environments have goals of achievement which can be handled just in terms of costs of actions and certain goals having pretty high reward. One other thing, of course, that gets to here is the last question. MDPs work only for ergodic environments. Are they making any assumptions about the environment itself? Must they have ergodicity for the environment or not? So MDPs work for ergodic environments. How many of you think it's true? Actually work only for ergodic environments. How many of you think it's true? Okay. How many of you think it's false? Okay. So remember last class we talked about terminal states? The whole notion of terminal state basically means the environment is not ergodic. Do you understand what I said? Okay. If a state is terminal, that basically means, remember what's the definition of ergodicity? Ergodicity says if you are in some particular state, the probability of going from that state to any other state in the environment is non-zero. So you can always basically get away, get from all the corners you fall into, get out of all the traps you fall into. But by definition, terminal states are essentially trap states that you can't get out of. Do you see what I'm saying? So that's how actually MDPs handle non-ergodic environments. Okay. In fact, one of the few things that winds up happening when you try to model a problem that is an A-star search problem, model a problem that's an A-star search problem as an MDP problem, you know that you need a RSAS' function which will capture the costs of the actions. You also know that some states have high reward, so you make those states high reward. But the question is, are you or are you not going to make those states terminal? Do you understand what I'm saying? Okay, if you do not make them terminal, then the agent can keep dipping into that state many times and getting lots of reward. Do you see what I'm saying? So they can essentially keep on going back to that state, and then every time they go, they get the reward. So if you don't want to allow that, you make that state terminal. Do you see what I'm saying? Okay. Whereas some other states, they actually may go back to those states. So for example, if you keep doing the action again and again and again and again, you incur that cost of that action again and again and again and again. That's normal. So that particular, every normal states, you just make them non-terminal states. But the goals of achievement states, these are kind of the nirvana states. And you can't keep on getting nirvana, then it will be just too much happiness in life. Okay, so once you reach nirvana, you're dead. Whether it's with a smiley face or bad, sad face, you're out. Okay, and to make that happen, you make those states terminal states. Okay, it's an interesting idea. In fact, you can talk about how to ensure, how to kind of model various problems as MDPs. It's quite clear that if the problem actually requires dynamic environment, you can't do it. If the problem actually requires partial and has partial observability, you can't do it. But in all these other cases, you should be able to do it. But how to do it right depends on understanding how MDP formalism works. Okay, so those are just a few things. We'll talk about more things later on, but you already see that things are kind of the formalism is very flexible formalism, and you see a lot of interesting connections to real life in general. Of course, real life is dynamic, real life is partially observable, so MDPs don't actually get there yet. Okay. And part of the reasons for this, as you'll find out, is that computational complexity issues come and bite you. We have forgotten the fact that this is a CS class for a while. We're talking about philosophy, we're talking about agents and their environments. Eventually, you're writing algorithms to compute these policies for these MDPs. It turns out we'll see that for an MDP with S number of states, the cost of computing optimal policy would be polynomial in the number of states. Okay, that itself is really sad actually, it turns out, because the number of states can be many. But if you have POMDs, the cost of computing optimal policy for a finite horizon POM-DP. Remember you talked about finite horizon MDPs today. You saw an example. We'll come back to it again. Finite horizon as well as infinite horizon MDPs are polynomial in the number of states in terms of the complexity of computing the policy. For POM-DPs, finite horizon POM-DPs have exponential complexity in the number of states. That means, basically, if there are s number of states, then the complexity is 2 power s. And it's sad enough to remember that if a state variable, if a state variable is, if there are n Boolean state variables, okay, n Boolean state variables, right, then there are actually 2 power n states. This is why saying it's only polynomial in number of states is actually quite depressing. Typically, you tend to think of states in terms of the properties of the states. Okay, if the states have, let's say, each state can be represented in terms of the n different Boolean variables, whether true or false, then the total number of states will be 2 power n. So the complexity of MDPs in terms of the state variables is already exponential. In terms of states, it's only polynomial. Again, this is something that you have to understand from a computer science point of view. Complexity is in terms of the input size. You can always make anything polynomial by just blowing up the input. Okay? So it's polynomial in the number of states, exponential in the number of state variables for MDP. For POM-DP, for the finite horizon POM-DP, it's already exponential in the number of states. That means it's doubly exponential in the number of state variables. Doubly exponential. And if you have infinite horizon POM-DPs, which we will talk about for MDPs too, it is undecidable. Undecidable. That basically means that there is no guarantee that the procedure for computing the optimal policy will ever terminate. So that's the kind of computational limitations that we would be butting our heads into as we extend the types of the MDPs. Once again, remember what I said about the difference between computer scientists and hackers. You need to know the complexity, but you shouldn't be depressed by it. Because the complexity results are only if you want optimal policies. If you want some random policy, you can just spend a few minutes and just say, this is good enough. If you can find a better policy, find it yourself. The only difference between computer scientists and hackers would just do that second step. Computer scientists will figure out first whether there is actually an efficient way to compute in polynomial time, the optimal thing. And if it's too hard, then they will give up and do what the hackers do. Okay? So life basically, POM-DPs are already double exponential, and things become just for finite horizon, and then undecidable for infinite horizon, and things become progressively worse when you start talking about DEC POM-DPs. Okay, life is a POM-DP. Actually, life is a DEC POM-DP, and DEC POM-DPs are life is too short to solve a DEC POM-DP in optimal way. You understand what I'm just saying? Okay. On one hand, our lives are DEC POM-DPs. There are multiple agents. Each of them are looking at the same environment and trying to optimize their return value. So these decentralized, partially observable environments, as soon as you have another agent, I don't know what's going on in their heads, and so it's partially observable world. So life is really a DEC POM-DP. Okay, if all of you just disappear, life is still a POM-DP. If you're there, it becomes a DEC POM-DP. It's never really just an MDP. And yet, actually life is too short to solve even a simple DEC POM-DP problem optimally. So you know that it's hard, and then you find out approximate solutions. Okay. So let's take the attendance thingy, and then we'll go forward. Okay, so the question for the attendance time is do you have a class before 9:40 a.m.? These are all, as some people have already started complaining in the anonymous feedback, these very intrusive questions, and as if I'm trying to figure out how to keep you from like 8 in the morning to hopefully 4:30 in the evening. But, so you can try to answer this. This would be useful at some point of time. We have to make makeup classes. Okay, so do you have a class before 9:40 a.m., which is basically before this class? Okay, so yes,
This is only for Monday, Wednesday that you're asking for.
but yeah. So I don't care whether we live, die, other days at all. In fact, I barely care if we are on 9:40. Now this is, again, as I said, I know that people are really worried about these kinds of questions. I did get like 2 angst-ridden anonymous feedback saying, this is not nice, you should not ask whether we are available or not. Obviously, you're trying to keep us beyond the time that we have given you to torture us. I have no real interest in doing that. Essentially, there will be classes that will be missing at some point of time. We will have to figure out, because some people are anyway asleep in the class, so we can do that here. So you have to figure out time is another one. Okay. So 115 out of 131, I'm going to stop this. Somebody who is still sleeping might have to get up and start move on. Okay, I'm going to stop now. Okay, that's all. I don't need it. I can use that. Again, as I said, don't be too worried. It's not that we're going to start. If in fact the majority are available, it doesn't necessarily mean that I'm going to start having these extra times before and after. I just know what. I did find that this class is actually available. I came the other day at 9 o'clock and there was like nobody in this class. So if I have to find a makeup class time sometimes, then it might actually be easier to do it in these times. That's the only reason I'm doing it. Okay, so I am going to go forward and talk about MVP formalism today, and okay, so as I said, MVPs are basically used for stochastic worlds and generalized rewards, generalized goals. Okay, and then so an action can take you to any set of states with a known probability at the time of thinking. When you actually do that action, it will do one of those states. This is why you can think of it as a game demonstration. Okay, only one of the states actually occur. Okay, but at the time when you're thinking about what are the actions that are possible, what are the good actions to do, you have to consider the fact that an action that has a very good potential, because it might take you to a state with a high reward, also has the possibility of taking you to a really low reward state. So then that becomes a question of risk averseness. And you get rewards for visiting a state. As soon as you enter the state, you get the reward. Okay? And then as I said, rewards can be thought, there are multiple models for MVPs. Normal model is just RS, that is, you just basically get reward for entering the state. The generalized version is RSAS dash, where you get a reward for doing a particular transition of going from S, using action A to go to S dash. Okay, and it's a question of reward function is specified if I specify these numbers. Okay, so the real question in MVP then is what is it that you're trying to optimize? Yes.
A quick question about the RSAS. In that case, is the reward, I guess, stored in S dash or in the A? Because
Just think of it as there is actually a table.
okay,
SAS dash table.
so you could get to S dash in multiple ways, but you wouldn't get to
Exactly. So this is allowing that possibility.
Okay.
Okay. This is way more general than what you probably need. Okay. So for example, RSAS dash can model just rewards which are just dependent on the state you get into. So basically, they will take 3 arguments, ignore the first 2, and decide what the value is. You see what I'm saying? Okay? So it's just, this is a more general one. And in general, one of the other things is, if you have an MDP with this kind of a reward model, you can compile it down to an MDP with this kind of a reward model. Which is part of the reason why we tend to just focus on reward of a given state kind of a models, because there are ways of compiling them down ultimately to the standard MDP model where you just get a reward in the state. Okay? When you say compile, what you mean is, given the problem with a particular state space and a reward function and a transition function, you compute a new state space, which is sort of in a polynomial time that is related to the old state space, but it's different. Okay? And in that new state space, the reward is just about the state S. Okay, so that's possible, because of which we just focus on this simple. Okay. Now, in general, one thing that you really want to get your minds around is, what is it that you're trying to achieve in MDPs? And the answer to that question is, what is it that you're trying to achieve in your lives? Right? You tell you, just increase your happiness, overall happiness. That's pretty much the only thing that one can say. Okay, so really what an agent is trying to increase is the cumulative reward it gets as it lives, as it goes from state to state to state. Living means going from state to state to state. Okay, and happiness is the reward that you get when you get into a particular state. Okay, so in general, basically, the formulation of MDPs is, it's an optimization over the cumulative reward that you get from the states you visit. And this is a little bit mind-boggling, because the specific states you visit are not completely under your control. You know, for example, what are the states with high reward, but you can't just directly go to them. You have to do actions to go to them. And the actions that you do, thinking that this action will take you to this high reward state, might actually take you to a different lower reward state because of the stochasticity. Given that what you are trying to do is optimize in a stochastic sense the set of states that you go through, so that in expectation, that means on average, the overall happiness you had in that, if you follow that policy, is the highest. Now, remember, people say honesty is the best policy. Right? People say this. And you know that only losers do honesty, because I know my friend Tom, and he was honest, and he said, yes, I was drunk when I was driving, and he got a really big ticket. So it's not a best policy. For him, it's not a good policy at all. Right? So the point there is that the specific rewards that you get when you follow a policy depend on the specific states that you wind up going to. So only in expectation, most of the statements like honesty is the best policy are in expectation. In the long run, over many, many lives of many, many people, honesty is a good policy, is the best policy. Of course, this has not been proven, but this is what they're trying to say. Saying, hey, look, I have a clear-cut counterexample. I tried to be honest, and similarly, if I say trying to copy this course is a really bad policy, am I saying that you cannot actually play a game with me and find a particularly nefarious way of copying which I did not actually detect? And then you can go back and say, look, man, I was so smart, I was able to copy in Rao's class. I was able to plagiarize in Rao's class. So it's, you guys can do it too. And then, 100 of your friends try to do it, probably 98 of them will get thrown out of the university. Because I will figure out 98%, it's just one of you I probably didn't figure out. Okay, so the question is, again, it's you decide the policy, the states that occur with respect to the policy are stochastic. For you, I didn't catch you, but your friend, maybe I'll catch them. And they have to take into account upside and downside in coming up with the optimal policy. I tell you, for this class, optimal policy is not to cheat. But you can try to recompute it yourself and see what happens at the end of the semester. Yes.
How do we, like, on what basis do we assign rewards for every stage?
That's a very good, very good question. That's essentially on what basis did you assign the cost for the actions in A-star search? On what basis did you on what basis did you given cost that A-star search actions? We just thought it was okay. So one of the interesting things is MTPs are close enough to life that people will start asking questions that they should have asked at A-star search itself. This question, you could have asked this at A-star search too. Who gives me the cost of the actions? It's not obvious. Okay? I'm just assuming that somebody gives it to me. And if nobody gives it to me, I have to learn the cost of the actions. And similarly, in the case of MTPs too, I assume that for the inference problem, somebody has given me the rewards and the transition matrices. The learning problem, which is what you actually deal with when you come into this world, is figuring out, as a kid, you try various kinds of actions, mostly involving putting everything into your mouth, and they have stochastic outcomes. Sometimes you live and it's like a sweet sensation, sometimes you die, sometimes you get bitter sensation, sometimes you get into all sorts of different states. Now there is a inbuilt reward metric to some extent for us, which is these pain sensations. And you convert those pain sensations into some sort of an expected reward for each of the states. Okay, you don't necessarily know that you're doing it, but that's one way you can model what you're possibly doing. And once I have the reward function and once I have the transition function, then the thing that makes a kid a smart kid versus a dumb kid is at some point of time they start actually using the model they learned of their world, as against still trying to work in the world and see what happens. Do you see what I'm saying? It's a very good question, but anyway, learning reward functions and learning transition models is what reinforcement learning is. That's it. That's basically connected to MTPs, and you can think of reinforcement learning as, here I assume that the model and reward is given, in reinforcement learning I assume that's not given, so I have to learn. So objective is to increase your cumulative reward. What is the solution? Solution is a policy. A policy is for every state you are in, what action should I do? Here maybe I go up, here I try to go this way, here I try to go this way, here I try to go that way. Okay, so a policy is a state action mapping. That's what it is. Now, the question then is, how many policies are there? Imagine there are S number of states in your MTP, and there are A number of actions in your MTP. What, in the worst case, is the number of policies that are actually A? It is, in every state S, you can do A actions, A different actions. A actions here, 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 and so on. So A times A times A times A times A, S number of times, which is